Our final lecture on heat engines is going to have to do with internal energy and heat engine efficiency. So one of the things that we need to make clear is the difference between internal energy and temperature. Yes, they're related, which is something that we talked about in class more than once now. But they are two different things. Internal energy is the kinetic energy inside a material. And that makes it different than temperature because temperature is independent of the amount of material. Temperature was the random kinetic energy or the average random kinetic energy of the molecules. So if we had more molecules, it didn't matter because the average kinetic energy didn't necessarily have to change, right? Um, if I have a piece of wood and it's at a certain temperature, and I have a tree and it's at the same temperature, that's perfectly fine because that just means that the average kinetic energy per molecule is the same, right? So temperature doesn't consider how much we have. Internal energy definitely considers how much we have, and that's important because with internal energy, we're going to see how much work we're going to be able to do, and we need to relate back to the work that gets done. So we have to consider how many atoms there are. For example, right, if I have a gas, and this gas is moving around, and in this case it's 362 Kelvin, that's its temperature, right? It has to do with the average kinetic energy of the molecules that are moving around. If I add more molecules and they're moving at roughly the same average speeds, well, I didn't change the temperature at all, right? Um, this still has the same temperature as it did before I put more molecules in because we really didn't change the speed, therefore we didn't change the average kinetic energy. The molecules are all roughly the same size, they have the same mass, and the molecules are all moving at roughly the same speed, so I didn't change the average kinetic energy per molecule, so the temperature was constant. But in this second part of that video, right, absolutely there was more kinetic energy because there's simply more atoms moving around that can hit other things and do work on other things, right? So as I add more molecules, the internal energy goes up, even though the temperature didn't go up because there's simply more there that has the ability to do work. Which brings us to our equation for internal energy. Well, internal energy equals 3/2 times N, which is N is the number of moles, which we talked about last lecture, the gas constant, times the temperature. And again, the temperature has to be in Kelvin. So everything we're working with, right, we're dealing with Kelvin really is the better place to work, right? Because Kelvin makes more sense to what we're doing, right? If we say we have a temperature measured in Kelvin, or let me back up, right? If we say that temperature is the measure of the average random kinetic energy, well, then it makes sense to use Kelvin because at 0 degrees Kelvin, there is no more kinetic energy. Celsius, Fahrenheit fall short because if we have a temperature of minus 10 degrees Celsius, well, that doesn't mean there's negative kinetic energy. That doesn't make sense at all, right? So Kelvin is based on what temperature's actually measuring, right? Kelvin's based on kinetic energy. So it makes sense to use Kelvin when we're trying to figure out energy flow and we're trying to figure out work, which is based on energy, and these types of calculations that we're doing. So 3/2 number of moles times the gas constant times the temperature in Kelvin allows us to calculate how much internal energy do we have. So let's do some examples and let's see why it's important to be able to calculate the internal energy. We're going to use one of the heat engine graphs, the PV diagrams from the last lecture. And this is the one that we use to calculate temperature and we use to calculate work done by and work done on the gas. So I'm going to walk through an example of how it's helpful to know the internal energy. So these numbers we calculated last time, right? We've said that at point A, it's 400.9 Kelvin. At point B, it's 2004.7 Kelvin, right? So if you go back and look at the last lecture, if you're not sure how we got those values, then it's there, but you should know because you just did homework problems on this too. So we're able to calculate the temperatures at A and B. Well, if I know the temperatures, and for this problem, we were assuming there was 120 moles of gas in this heat engine, then I have everything I need. I have the number of moles, I have R, I have the temperature. So knowing all that, I can calculate how much internal energy there is, right? At A, there is 600,000 joules of internal energy. That's the energy inside the gas. It's not doing anything yet, but it can, right? And at B, there is 3 million joules of internal energy inside the gas. So I can calculate the energies, right? and that's the energy inside the gas. Now, let's take this problem a little farther, right? That's just using the equation that I gave you. I was able to calculate that. 3 halves times 120 times 8.314 times the temperature of 400.9, right? And then the next one, same thing, except it's a temperature of 2004.7. So you could calculate those yourself, and you can see if those numbers are right, but they are. But let's think about this. What else were we able to calculate for this graph? Well, we were able to calculate the temperatures, which now gave us the internal energy. But the other thing that we were able to calculate is we were able to calculate the work, which was the area underneath the line AB. So I know when this heat engine went from A to B, I know it did 1,600,000 joules of work, right? And we calculated again last lecture, 1,600 joules of work was done going from A to B. I also know that the gas had 600,000 joules of energy at A, had 3 million joules of energy at B, so that means that the energy inside the gas went up, and it went up 2,400,000 joules. So the gas did work, and it gained energy in the process. Well, we know work by the gas usually means that's energy it gives away. But if the gas gave away 1,600,000 joules of energy in the process of doing work and still ended up with 2,400,000 joules of energy more than it had at the beginning, well, then that means how much heat flowed into this engine from A to B? Well, 4 million joules of heat must have flowed in. I'm going to say that one more time just to make sure it's clear. As we go from A to B, the gas itself has 2,400 joules of energy more than it had before. Along with that, it did 1,600,000 joules of work, which means the heat that flowed in must have been 400 million. And let's see. And what I just did in that last example is really just an application of this equation that we started heat engines with, right? The change in internal energy equals the heat in minus the work by. Well, if we know the change in internal energy, we know the work by, we add them together, it's got to be the heat in. So we can figure out how much heat had to flow, right? And where did that heat come from? So in a car, it comes from burning gasoline and other things. It's still probably burning something, right? There's more engines out there than just cars, but cars is the biggest one. So we know how much heat the whatever it is, right? The fuel has to produce in order to make all of this happen, for this particular heat engine. So now we can calculate the internal, well, we can calculate the temperature, we can calculate the work, we can calculate the internal energy at different points, and all of those together will allow us to calculate the heat flow, which now means we really know everything we need to know about the engine, right? We know how much heat has to be produced to make this work, we know how much work we're going to get out of it, right? And we know the temperatures it has to work at. So we know quite a bit about it, which brings us to our last thing that we're going to look at, which is efficiency. In all cases, what is efficiency? It's the measure of what we want to get out of something divided by what we want to put into it, right? That tells us how efficient it is, right? So if we can measure what we're getting out of it, and we can measure what we had to put into it to get out of that, well, then we can get efficiency. And that shows up all over the place, right? For example, a light bulb, especially old style light bulbs, right? A 100-watt light bulb is incredibly inefficient because what do we want to get out of it? We want to get light out of it. Well, we don't get a ton of light out of it, but we have to put in an enormous amount of electricity, right? So a light bulb, we put in electricity, we get out light. We can see how efficient it is. And again, old style light bulbs that get hot, very inefficient because we get a small amount of light for a lot of electricity. But there's plenty of other examples. Your stove, same thing. How much electricity do we put into it to get out the heat we need to cook with, right? So, we can go all day and come up with examples, but efficiency in essence is always that, right? It's what we get out of it divided by what we have to put into it. Well, a heat engine, what do we put in? We put in heat and we get out work, or we get out motion, right? And really, there's always been talk about making cars more efficient, but are we making cars more efficient? Well, in the end, for a car, we're getting out motion and we're putting into it gasoline, right? That's in essence what we're doing. So lots of times we want to talk about efficiency for a car, then we're talking about miles per gallon, right? And Are we getting more efficient when it comes to that? I would say probably not, right? If we look at it, the Model T, which was one of the first cars made, at least one of the first cars mass produced, had a miles per gallon of 25 miles per gallon. Now that's the maximum that it got, or that's kind of the best that they can expect to get out of the Model T Ford. But still, it got 25 miles per the gallon. And if we think about that and how that compares to these days, we really didn't do that much better. Um, our cars aren't much more efficient if we think about how much gas we have to put in to how many miles we get out of it. Um, Now, does that mean that the engines haven't improved over these years? No, they have, right? Things have changed, right? And the biggest thing is we haven't tried to become super efficient in the same way that we think about it, purely like this. And what do I mean by that? Well, first of all, the Model T Ford was slow, right? The top speed it can get was 45 miles per hour, right? So you never got up to the speeds that cars get to today in a Model T Ford. So as we go faster, the efficiency of an engine goes down. If we want to be really efficient, the best thing we could do is drive slow. And that increases our efficiency. The other thing is the Model T Ford wasn't very heavy, right? It had a light frame. It didn't have a lot of additions to that frame, right? There wasn't much to it. There were seats, and there was basically a metal case that held, all the components that made the car move, and it kept you inside there. So there wasn't much to the frame of the car, which made it extremely unsafe. If you were driving at 45 miles per hour, you're basically taking your life in your hands because those tires weren't made super well. And if you hit anything, then that was it, right? Because you couldn't recover from that because there's no safety devices in there. So, as we try to become efficient, the other thing that we try to become is more safe. And cars are designed, they're designed heavier, they're designed with more components to allow you to be safe, right? They're designed with a lot more. So it makes it harder for the engine to do what it has to do because it's carrying a bigger, it's carrying a bigger chassis, it's carrying a bigger frame and body and everything else. Um, the other thing was the Model T Ford focused on one thing. It focused on making the car go. And that's partly what made it more efficient. It got more miles out of the gallon, right? You think about it now, you have a car, well, a car has an air conditioning unit, which has nothing to do with making it move, right? It has a radio or a CD player, it has a heater, it has power windows, it has power seats, it has internal lights, it has it has tons and tons of things. And every time we add one of these things, or every time we use one of these things, right, our car efficiency goes down because some of that gas that we're burning, it doesn't go to making the car move. It goes to um, these other things that aren't making it move, right? So the less things you have on while you're driving, the more efficient you're driving, right? And then the last thing is the engine was just, which kind of goes to the low miles per hour, right? It was a small engine and it was just designed to make the car move. Um, Whereas now, no one uses a 200 horsepower engine in their car. That would be ridiculous, right? Most of us have way too much horsepower than we need, right? But that's kind of where we're at. Right? If we think about it for a while, um, you could look this up yourself, but the miles per gallon, especially during the recession, were going up and up and up and up, and cars were becoming more and more and more efficient, and they were getting more miles out of the gallon. But really, since the recession and where we are now, um, every year the miles per gallon has actually gone down. The cars have become less efficient. Why are they less efficient? Because one, we're driving bigger and bigger cars, right? And matter of fact, a lot of people aren't even driving cars; they're buying trucks and SUVs and bigger vehicles like that, which is all affecting our efficiency and making it go down, right? And people are buying things that are faster and more powerful, right? So efficiency has kind of gone out the window. Um, and we're doing less and less. We're buying cars that are less and less efficient because we want the other things from a car. We want speed and we want power. We want them to be big so we can carry 6 people with us when we're driving, right? These are all the things that we're leaning towards. And with that, we're sacrificing efficiency. But let's look at this in terms of a heat engine, whether it's a car or not. We say efficiency is what we get out of it divided by what we put into it. Well, what we get out of it is work, right? Work by the engine. So work by the engine is the efficiency, or is what we get out of it. And what do we put into it? We put heat into it. So we could certainly say that efficiency is work by divided by heat in. And I know that we didn't use H in class, but that's why I'm saying it in words, right? Work by divided by heat in. So that's the case. Now, the other one, though, if we think about it, well, if we go through an engine, and it doesn't matter if it's a car engine or not, if I go through a heat engine, every time I get to A, I'm back to the same temperature. So that means every time I go through a complete cycle, I'm back to the same temperature, which means my change in internal energy is 0, or my net change in internal energy is 0 every time I go around this cycle. So with that in mind, I can definitely say that the work by must be the heat in minus the heat out, right? Because I put heat in, I do work, I take heat out, right? So in the end, this has got to be the case. The work by the engine must equal the heat in minus the heat out. And then that's still divided by the heat out. So I could say efficiency is also this, right? And in both cases, we could look at that, right? Now that we can calculate internal energy, we can calculate the work by an engine. We can calculate the overall heat that had to go into the engine, right? We can calculate these things and we can get the efficiency that way, right? So we should be able to calculate the efficiency if we have a PV diagram. The other thing to point out, though, is that every single let me actually back up first to that. The other thing we could point out is the more heat we take out of this, the less efficient the engine is, right? If we look at it, right, if we agree that work by must equal the heat in minus the heat out, then in a complete cycle, right, then the greater the heat out is, the less efficient the engine is, right? So as we have to take away more heat during a cycle, the less we get out of the engine. If we think about it for a car, right, you have systems in there that remove a ton of heat, right? Your whole coolant system removes an enormous amount of heat, which means the car is not super efficient because we're burning gas to create heat and then we're removing it in this coolant system, right? Your exhaust removes a ton of heat. And again, right, we create all this heat and we have these two systems that their main jobs are to get rid of all that heat that it's not using, right? Which means the car engine not super efficient. But the other thing to say is, it doesn't matter what heat engine we have. If we look at the PV diagram, right, the PV diagram proves that we have to remove heat. So if we go back to the same one I've been using for this model, A, B, C to D to A, I know from B to C there's heat flowing out. And I know from C to D there's heat flowing out. And there has to be heat flowing out or this heat engine isn't going to work, right? Even though we know removing heat makes a car less or makes an engine less efficient, we also know at some point we have to remove heat. It's just impossible not to remove heat, right? Because if we let the gas do work and we don't cool off the engine and we just push the piston back up to get ready to do work again, we're not getting anything out of it, right? So it's one of the things we started this in class with is the idea that we let the gas do work under high pressure, but then we have to lower the pressure when we reset the system, right? And as we lower the pressure and reset the system, from C to D, it's important. It's important to be at a low pressure because we need to make it easy to push the piston back up. But if we have to make it easy to push the piston back up, we have to remove heat to do that. As we remove heat, we lose efficiency, right? So if this was a heat engine that we were using, right, here and here we're removing heat, which again, it's important, or the heat engine doesn't work, but it's also affecting efficiency. Same thing here, right? This is a different heat engine, but still, from C to A, we are removing heat because we're resetting the system. So when we reset the system, we have to remove heat either before or while we're resetting the system, which means efficiency goes down the more heat we have to remove, right? I mean, in a perfect world, not in a perfect world, but in a perfect engine, which doesn't exist, right? Then all the heat we put in would heat up the gas, and then as it pushes the piston down, it gets rid of all the energy that it got from the burning gas, and then it's back to being cool gas, and then you could heat it up again. Now, it's just not going to happen, but that's what the case would have to be. Now, understanding that tells us one thing, which is really the second law of thermodynamics, or the second law of heat engine. No heat engine is 100% efficient. That's impossible. It's impossible for something to be 100% efficient. We'll never put in, a certain amount of energy by burning gas and get that amount of energy into making the engine move, right? It's simply impossible. But if we had a heat engine and it was running and we wanted to see what the maximum possible efficiency is. That doesn't mean that's the efficiency that it acts at, right? The efficiency that it actually has, because, as I said, for a car, efficiency is affected by a lot of things that the PV diagram can't help us with. But the maximum efficiency that we could ever possibly kind of strive towards is what we call the Carnot efficiency, right? The Carnot efficiency is the maximum possible efficiency. And we could get that efficiency if we knew the maximum temperature, the hottest or the highest temperature that the engine's at, which again we can calculate, and we subtracted the coldest temperature, which again we can calculate and divide by the hottest temperature. So that's something else that we're able to do, because if we looked at a heat engine, right, we can calculate the temperatures at all these different spots, and therefore we could calculate what's the peak efficiency this engine could ever possibly hope for. And again, even the peak efficiency is not really obtainable, but at least it's a more realistic goal than saying, hey, 100% is what we're looking for, because that can't happen. All right, so that is a discussion on efficiency with really 3 equations for efficiency. What's our maximum possible efficiency, and what are our actual efficiencies within the parameters that we have. So we can calculate efficiency. We can also calculate internal energy, which is going to allow us to calculate these efficiencies if we need to, and also just give us an understanding of how much gasoline we have to burn, right? If we know something needs 4 million joules of heat, well, then we can go and say, okay, well, we're burning gasoline. How much gasoline do we have to burn to get that? And that's not too crazy of a calculation, right? That's really things we could look up, right? How much energy is released, and it will give us values, right? If we're burning wood and we're burning, then we get this amount of joules per second based on this, size piece of wood or this mass of wood. This mass of wood will give us this energy per second. Gasoline, this mass of gasoline will give us this energy per second, right? So figuring out what's going to give us this amount of energy in the time that we have, the time that it takes to go from A to B, right? These are all now realistic things, and we can really get an understanding of what we have to burn and what we need to get these things. All right, so hopefully that all makes sense. We'll be posting problems on Long Kappa for these other parts too. I'm going to have them up for the weekend, I hope, so you could start them on Monday. But you have stuff now that you need to do.